did was we took each of those and we got our decay ratios, whether it's monotonic or oscillatory, our settling time, our offset, and our overshoot. This one, you could kind of find an offset, but it doesn't really ever have a steady state value because it just keeps going because that's what it does at ultimate gain. But if you wanted to, you could say the offset was just kind of, you could take the middle, the difference between the set point, which is in red, in the middle of the model, or the experimental, which is, I kind of use that value to find the overshoot. So the overshoot is just your difference between, so let's say for the experimental in blue, it's the difference between the steady state value, which we'll just call the middle here, and the peak, the first peak, divided by the difference between the middle and the original steady state value before the jump, which we got 59% for the experimental and 237% for the model. For the quarter decay, I'll show you how we did the settling time and the offset. The quarter decay is just when it decays this here from the middle up to there is 1/4 of the distance from the steady state value to the first peak, which in the model is pretty accurate. In the experimental, it's a little different, just because no system is perfect. And I also should note, mine looks a little different from some because my input power range was kind of small, so I didn't have a very big jump, and so it's not as perfect. Like right here, we have noise in the system, but mine oscillates so quickly. It's like right here you have a frequency of about about 5 hertz because the period is only about 0.2 seconds. So the noise really plays a big role. Like right here, it's really a steady state. Can't really tell, but if I carried this on further, it still looks the same. It just keeps doing that, and it's just noise, but it's done oscillating. And then the settling time is just how long it takes to get to here, which is about 0.9 seconds for the model, and it was about 0.7 seconds right around here when it kind of settles out for the experimental. This is our 1/10 decay, which just means that the difference between this peak and the final steady state value divided by the difference between this peak and the final steady state value is 1/10. Our experimental kind of jumps around a little more, and I know it looks weird, but if I keep going, it just keeps doing the same thing, but it's just noise, like I said. But they do jump to about the same point. They look kind of similar. 1/500th decay. Can't really tell. And the decay ratio is so small for the model, you wouldn't really be able to tell on the experimental with all the noise. So I just call it a 0 for the decay ratio for the experimental because I don't know how to really figure it out. Because it's just, I would just be guessing really. And then this is the critical damping, which is where it doesn't have any overshoot at all, and it rises and then finally hits its peak, which you can see there's big offset. The higher your KC value is, the less offset you have. Here we have a really large offset. Obviously the model is a little bigger than even the experimental, but that's because it's such a small KC value. So it's good. Your client wants you to have as little offset as possible, but they also want you to not have tons of overshoot a lot of times and just go all over the place, so you kind of have to find a balance between the two. Of course, that was all for our proportional only controller. I forgot to mention that. So in conclusion, I'm not going to go through every single one of these values, but you can see that our model decay ratio is really similar. For the 0 to 69%, 70 to 80% input or power range, they were identical. They were just slightly different for the 69 to 70%. Our experimental decay ratios were actually pretty good. I mean, there's a little bit of difference between the model. Like here, it's 0.25, here it's 0.5, but they're pretty similar. I mean, the 1/500 you can't really, with the experimental, you can't really. It's not precise enough to go all the way to the thousandths place, so we just call those 0. our settling times, you'll notice that they generally decrease the lower your KC is, because this is where your KC is highest, this is where it's lowest. You'll see they pretty much all decrease as you go for the models, and the same for the experimentals, except in the 0 to 69% range is a little different. Okay, our offset, like I said earlier, the lower your KC value is, the greater your offset's going to be, and that's definitely the case for all the model, except I think Ray had his values backwards there. But for everything else, you see they're increasing. Yeah, the experimental, correct. They're increasing every time you go down. In this one, it appears that the 69 to 70% range have the smallest offsets, and the 0 to 69% range have the largest offsets. Our overshoot percent, for the 69 to 70% range, we got some weird numbers just because it's just really, it's only a 1% input power range, so it's just, the data is a little wild. But you can see, and also for the 0 to 69% range, the experimental just didn't work the same exactly as the model did. And it doesn't take a lot. I mean, 1/10 decay isn't a whole lot, and so you can just be off by a little bit and it not really show up on the experimental. Or it's really, the experimental is hard to read with all the noise in our system. But you can see they generally, though the overshoot decreases, the lower your KC goes, and eventually critical damping, you have 0. In conclusion, each input power range had a unique KC value for the different responses a client might want. As KC increased, the offset decreased, the decay ratio increased, the settling time increased, and the overshoot usually decreased. Does anybody have any questions?
Can you show us your SSOC again?
Yes, sir. This is our SSOC. It's just, we took a bunch of steady state responses at, with different inputs. So say right here we took a 40% input and we measured the final steady state output. We were able to make a graph of each of those trials. And you can see from 0 to 69 or so, it's fairly even. It kind of starts out flat and then raises up and increases a little more, the slope increases. But from 69 to 70, it's wild. And it's just got a really, really high slope there. And then for 70 to 80%, it's about 3.1 volts per percent. There's a little bump here. But from here on, it's pretty linear.
What's those green dots for?
The green dots are, it's where I kind of threw them in there because you had asked for the difference when we take a step down between our normal steady state value and what happens when we take a step down. And what happens is it requires less input to get an output on the step downs for some reason than it does for the steady state responses. So here the green dot is about 64% input, yields you 40 volts, and at about 71 yields you about 56 volts, when normally it would take about 73. Any other questions?
Surely somebody has some questions about that you just told us about. Nobody, everybody understands that clearly?
The system behaves differently stepping down.
Is that what you're saying? System behaves differently if you step down than step up?
Yes, sir. I think it might be attributed to hysteresis, but I'm not entirely sure.
What's that?
It's we learned about in material science. They showed us a hysteresis loop that shows it basically data behaves differently whether you're increasing something or decreasing something. So if you're increasing something, it might go like this, and if you're decreasing, it goes like that, and ends up with slightly different values. But I'm not exactly an expert on that, so don't quote me on that.
Huh. Makes sense.
You say, huh?